Hello everyone, good morning and welcome to the Bangalore International Centre. BIC is an inclusive and neutral platform for informed conversations, exchange of ideas, arts and culture. And today's session is Swing, Reverse Swing, Knuckle-ball, Aerodynamics of a Cricket Ball. Sanjay Mittal's presentation begins with an intriguing comparison of how air flows around projectiles in various sports, even though the title only alludes to one, from the spinning flight of a soccer ball to the subtle aerodynamics of a golf ball. He'll go on to explore how synthetic shuttlecocks differ aerodynamically from the traditional feathered ones. Cricket fans can look forward to a deep dive into the mysteries of swing and reverse swing, and can a new cricket ball actually reverse swing? Professor Mittal answers these questions by presenting results from the wind tunnel experiments and large eddy stimulations. To wrap up, he'll dive into the aerodynamics of a frisbee. His lecture will be followed by a Q&A with the audience, after which our invitee for today, Mr. Javgal Srinath, will offer his comments. This lecture is part of Raman Research Institute's Vignana Kathikalu, which is a series of popular talks on science. Before I invite Professor Tarun Sauradeep to introduce the speaker, may I request the audience to either switch off your mobile phones or put them on silent for the duration of the session. If you'd like to take pictures or videos, kindly do so with your flash off. Now, to introduce the speaker, I'd like to call upon Tarun Sauradeep, the director of the Raman Research Institute.
Good morning. It's a great pleasure to bring to you a new dimension to our science talks, where we are touching the science of sports. And I'm also glad that we have a personality like Javgal Srinath in person here in our midst for this talk. I hope that this will bring the society together in terms of the different things that we do in our own lives. And my introduction will say, Professor Sanjay Mittal is one of the leading computational fluid dynamicists in the country. This is not from anything, because I know him so well that so he has been very, very instrumental in pushing the landscape of computing capabilities in the country. Particularly aerodynamics is one place where this is very heavily used. And so his interests include fluid structure interactions, flow-induced vibrations, and aerodynamic shape optimization, various things that anyone in his area would do. But he also has another aspect to him, which is as strong as his research interest. He's a very disciplined guy, and you'll know why I can say a lot of things about him a bit later. But he is a very passionate teacher. He's been at Indian Institute of Technology, Kanpur, IIT Kanpur, for many years now. And he's one of the leading researchers who's won all the awards. I won't bore you with all that. But he has a love for sports. So every day he plays badminton. He does it religiously. I think what happens is his partners have aged and retired out, but I understand that younger people come in and play with him every day. And in that, he has translated that to his own work and computational fluid dynamics. And IIT Kanpur, like many of our undergraduate places, of course, it's very easy to get excitable undergraduates. So he's harnessed them, and he has done something where we are trying to take, I can tell you, he's one of the experts of computational fluid dynamics, working with, on a subject which is our national passion, right? Cricket. So I think that's a lovely way to bring the country together. So Sanjay Mittal received his undergraduate education in aeronautical engineering in IIT Kanpur. He went to University of Minnesota for his graduation, and he has been the professor at IIT Kanpur in the Department of Aerospace Engineering since many years, from 90s maybe. And this is very nostalgic. The picture is from landmark picture of IIT Kanpur's library, iconic picture, I would say. And I love it because we were minted in the same institute in the same year, and we actually got in and had neighboring rooms when we first joined. So it's been, it's a great pleasure to see someone who we know well grow to such levels, internationally acclaimed guy. And so he is a fellow of the Indian National Academy of Engineering, National Science Academy, Indian Academy of Science, of all the four academies, and he is a Bhatnagar Award winner, and I think Swarna Jayanti and many others. So you can just rattle off. So I won't come in between what promises to be a great talk. So he's going to tell us about swing, reverse swing, and knuckleball, and dynamics, aerodynamics of a cricket ball. So no further ado, let me invite Sanjay for his talk.
Thank you so much, Tarun, for these warm words. It's absolutely delightful to be here. Tarun is such a great friend and a great host. And when he informed me that Mr. Javagal Srinath will be here, I'm actually very nervous. I'm shivering in my pants. I feel like a student who's when I was a grad student, we had to write some comprehensive exam and also give some. So that's the kind of nervousness I have. But sir, it's an absolute privilege to have you here and to talk in front of this audience. Uh, so as Tarun said, this is an iconic picture of IIT Kanpur, the Central Library, and we celebrated 50 years a few years ago. And on that occasion, the institute brought out a postal stamp, and the picture is taken by a colleague of mine, Dr. Pal. Unfortunately, is no more. And this picture actually appears on a postal stamp. I like this picture a lot because it says, it reminds me of what research is. So you see the library, and then you see a reflection of that in the evaporative cooling pond that we used to have for air conditioning. Now, Tarun, that's gone. But research is all about reflections. You do a piece of work, then look at it, do some more, look at it again, and so on. I've been very fortunate at IIT Kanpur to be working with the young students. So most of the students who have worked on these projects, which I'm going to show you, are undergraduate students. Some have joined a degree program, like a bachelor's and a master's, but mostly undergraduates. So that's even more gratifying. So what I want to talk about is give you some concepts of fluid mechanics. I'll try not to bore you too much, but some of them are a little bit essential to understand the science of these very nice projectiles. And we'll look at three projectiles, time permitting. A badminton shuttlecock for sure, because I play badminton, as Tarun said, and there were some questions that came to my mind when we were playing badminton. Then we'll talk about the cricket ball, and if time permits, then frisbee. So first, the journey started with the question that came to my mind as an aerodynamicist is that how do these different projectiles compare? So you have different games, golf, you have cricket. So listed in this picture are these projectiles. These are all Olympic standards. So there's a baseball, there's a tennis ball, then golf ball, then the hockey ball. So hockey ball and golf ball are actually very similar except for the size. Both have dimples on them, and I will say a few words about it. Then of course the cricket ball, then this is the Adidas soccer ball, the volleyball, and these two shuttlecocks. And the first question that I wanted to ask myself is, how do these aerodynamically compare with each other? Can we come up with a framework where one can say, okay, this is a projectile that has this aspect? And so we came up with some wind tunnel tests, and the summary of it is the following. So on the x-axis is something called a Reynolds number, which is just a non-dimensional speed. So I'll come to this in a little later. So for each projectile, the speed of operation is different. So if you want to compare them, it has to be, you have to compare apples with apples. So that's the Reynolds number. I'll explain in a minute what the Reynolds number is. And the vertical axis is the drag coefficient. So it's not the drag, but it's a non-dimensional drag. Again, I will explain this in a minute. And this is a sphere, a smooth sphere. So you will notice that at there's a relatively large drag at low speeds, and then at high speeds the drag really becomes very tiny. Okay, so that's because the boundary layer on it goes from a laminar to a turbulent state, and you will see that in almost all the projectiles. For example, if you look at a golf ball, so this is your golf ball. Okay, so there is a high drag at a low speed, and then at higher speeds the drag is low. But this transition where the drag goes from a high to a low value shifts to a lower speed. And that's because of the dimples on them. So I'll explain you why golf balls are actually dimpled. Here's your tennis ball. The tennis ball always has a very high drag compared to any other projectile because the fluff on it, the felt on it, creates a lot of drag. And a tennis ball is extremely interesting. So you take a new tennis ball, the fluff is intact. So you serve and it goes really quick. It has low air resistance. And as it becomes older, the fluff thickens up. So it will have more drag. So you will see players, they ask the ball boys or the ball girls, they'll ask for 5, 6 balls and then choose a couple of them. And I used to wonder, is this a fashion thing or they are making some statement? What is it about? So actually they are checking the tightness of the fluff. And once the ball becomes relatively old, again the drag will reduce. So it's become very smooth. But then it doesn't bounce as much and a lot of other things happen. So if you really want to be a good player in terms of good service, then along with your skills, maybe this knowledge also helps. Here's your badminton shuttlecock, right at the top. So there are two shuttlecocks. There's a duck feather, which you see the drag coefficient remains almost constant with speed. And then there is this plastic shuttlecock, the nylon shuttlecock, which you see the drag changes quite a bit. So if you hit a smash with a nylon shuttlecock, it actually travels very quick. Okay, the shuttlecock offers much less air resistance as compared to a duck feather shuttle. So the question was, why is this happening? Why are we not able to make shuttlecocks which exactly mimic a duck feather shuttlecock? So coming to that, first let me show some things that we found on a duck feather shuttlecock versus a nylon shuttlecock. So this is my favorite player, Lindan. You can imagine this smash really goes quick. In the fastest smash is in excess of 550. It's actually faster than a bullet train, okay, faster than the Chinese maglev. And this device weighs only 5 grams. So it's an amazing engineering device. The duck feather shuttlecock is made out of course, the feathers of birds. So they're very light, they're extremely strong, and that's why this device is extremely light. The problem is these feathers are brittle. So you play with them for about a game or so, and you are going to lose the shuttlecock, so you have to go to a new one. So it's very expensive, okay? And then there is the cruelty to animals. You can't have entertainment at fun of some other organisms. So there's been a lot of effort on coming up with a synthetic shuttlecock, a nylon shuttlecock. And this device is absolutely amazing. I think it's one of the finest engineering devices that is built, and full marks to Yonex. A duck feather shuttlecock has a certain drag, and those of you who have played badminton, you will notice it auto-rotates. Okay, so it's because the feathers are overlapping each other. If you see these feathers, they overlap each other, and they are actually at a small angle to the flow. So the shuttlecock, you can imagine, is traveling up. The flow is coming on it from top to bottom. So the flow hits these flaps at an angle. So there's a small force that is generated on each of them, and they give a moment, a rolling moment. So these devices will auto-rotate. Okay? And you would like these devices also to auto-rotate. That's important from a stability point of view and also from an aerodynamic point of view. In fact, if you notice a shuttlecock, it has an asymmetry in it. There are these little panels that are jutting out, and the holes, the pores that you see on the two panels, they are not symmetric. One set is larger than the other. Then there are these spikes. They also are at an angle. They are not symmetrically placed. So there's a lot of engineering that has gone into it. Anyway, we wanted to look at it a little bit. So the first thing I asked some of the smart undergrad students we had, that why don't you make an AutoCAD model of these off-the-shelf devices and run CFD on them, computational fluid dynamics, and let's see what comes out. So they took this Mavis 350, which is the nylon shuttlecock. the Aero Sensor 2000, which is the feather shuttlecock. And then I said, okay, these gaps probably are playing a big role in, the fluid goes in through the shuttlecock. So maybe we seal the skirt, the gaps through the skirt. So you make a shuttlecock which is like the frustum of a cone, but it is hollow inside. And my guess was that this would have a very large air resistance, okay, compared to these two, because this is more like a bluff body. It blocks the air, so it would have a lot of air resistance. Okay, and then let's see the aerodynamics. So these kids ran the calculations, and I'm just showing you one of the pictures. So this is a cross section of the shuttlecock, and you see the velocity, and these are velocity profiles as we call them. So if it's a uniform velocity, it would be just straight, and then these little changes that you see from uniform flow are because of the wake of the shuttlecock. Okay? They are color coded. Blue means it's slow and reverse flow, and the red means it's a large speed. So the speed is 50 meters per second. You will see this gapless shuttle has a very big recirculation zone. Okay, so indeed it gives a lot of blockage to the air. But if you see in the far wake, it goes towards a uniform flow much quicker than the others. Okay, so the first surprise was that actually this offers the smallest air resistance amongst these three. So if I show you the drag coefficient, which is the non-dimensional drag with speed, so you can forget this axis, just look at the numbers. The gapless has the smallest resistance, then comes the feather, and then comes the synthetic. Okay? So the question is, what then creates the drag on these shuttlecocks? And what we found is, through our analysis, that if you, first of all, the pressure is what creates most of the drag, and the viscosity, the viscous effects, they create very little drag. That was expected. The more important point was which part of the shuttlecock creates the maximum drag, and it turns out this number 4 and 5, they are responsible for almost 75% of the drag on the shuttlecock. So these two, the outer skirt is creating the maximum drag, and it's a very cute aerodynamic phenomena. So you get a pressure on the inside, you get a pressure on the outside, and the difference between them at the places where there is a solid object. So where there is a gap, there is no contribution to drag, but wherever you have a solid wall, the pressure difference between the two has a component in the direction of the speed, and that's what gives the drag. So essentially these devices would create air resistance based on the pressure difference on the inside and the outside. Okay, so that's one clue that we got. So we looked at the pressure distribution along one of the rays of this shuttlecock. So that's the nylon one, the synthetic, the feathercock one, and then the solid one. The red lines are the pressure on the outside, and the blue lines are the pressure on the inside. So first observation, these shuttlecocks, the nylon, they have a distributed pressure difference. Okay, whereas in the feather shuttlecocks, the gaps are large, so most of the pressure difference is at the feathers. Okay, so that's one very big difference, the way the drag is generated. And of course, here the pressures are relatively similar. Of course, it's distributed, so they generate much less drag. Now coming to the why, the good players would prefer playing with a duck feather shuttlecock. So imagine now, I have this shuttlecock flying, and one of these feathers, it goes bad. Okay? So the change it will make to the flow and the pressure difference it will cause will create a much larger moment about the center of gravity for a duck feather shuttlecock compared to this, because this is all distributed. So even if it gets torn a little bit or gets damaged a little bit, it doesn't make much difference in the moment. So this device will now move around a lot, and it's more difficult to control. And you can do that only if you are a good player. Okay, so you can get a feel of, and the shuttlecock is changing throughout the game. The feathers are getting ruffled, no pun intended. They're getting broken, so you have to be a good player to control it. And that's why people usually who play with these, they found these very boring. They said, it's not the same. A question that was not clear from these simulations is, okay, Yonex is very smart. They are making these shuttlecocks. But why would the drag of these two shuttlecocks be different? This at small speed, this drag is so large compared to this. Why can't they be tuned? And then we realized actually they are very smart. This is what they did probably. If you look at a duck feather, it retains its shape. So this is a low speed, only about 30 kilometers per hour. This is about 250 kilometers per hour. You can see the cross section is almost circular. Look at the nylon shuttle. Okay, it buckles and it gets almost a square cross section. Okay. So it deforms and the drag reduces. So actually the cross section area changes and it just flies through air. If the Yonex guys would have put this drag to this value to begin with, then for smashes this drag would be much smaller. So they have sacrificed the design point. So they are saying let's tune these shuttlecocks to something like 100 kilometers per hour. So at that speed they would behave identically, okay, or almost identically, and at off design speeds, which means lower and higher speeds, they would not give a very good performance. So we decided to find out why do these shuttlecocks deform the way they do, and can something be done about them? Can we come up with better designs? So that's the final goal. We are not there yet. We are still trying to understand why these shuttlecocks behave the way they do. So obviously these shuttlecocks deform. So we must couple the structural analysis with the fluid mechanics. So now we solve the equations of fluid mechanics, the equations of structural mechanics, and pass information between them and do this in time. So this is a mesh that is created for the structure. Then you have a mesh for the fluid. They talk to each other. And this is a shuttlecock. So all this is now spontaneous. So this is a shuttlecock traveling at low speed. This is at high speed. And the analysis actually gives this buckling shape where you get almost a square cross section. So now we can get more details about it. So this is the speed. This is the drag coefficient. That's what if the shuttlecock would have been rigid, the broken line. The red line is when it is actually a deforming shuttlecock. So with speed, the drag is reducing, and at some point, it starts reducing at a much higher rate. And in fact, up to here, the shuttlecock retains its shape. Then it becomes almost a squarish cross section. And in fact, if you increase the speed more, so a harder smash, you see the skirt actually starts vibrating in the radial direction. And if you increase even a harder smash, then there's a traveling wave. So these vibrations are actually traveling around much like in a compressor of an airplane. Okay. So just to show you some pictures, so we are looking at a shuttlecock which is facing us. The cork is inside, behind the screen. So we are staring at it. The color scheme is, the blue color is very low deformation, and the red color is about 3 millimeter of deformation of the shuttlecock. So at low speeds, it remains almost circular. Then you see it starts buckling, and then you get the vibrations, and then you get a traveling wave. And you can see this in these pictures. So these are at different times. You can see the shape of the shuttlecock is changing in the circumferential direction. This is how so far the calculations, the blue line, they compare with the black line. So the black line is experiments. This is the modeling. And we are doing quite well actually now. Okay, so we are able to capture the point of buckle. We are able to capture the shapes, look at the material properties and so on. So the hope is maybe in future we can come up with better shuttlecocks. But still the analysis is not complete, because so far we have assumed these shuttles are not spinning. So they are stuck at some point, and you just have a flow coming in, but real shuttles are spinning. So we said, okay, can we measure the RPM of these shuttles during auto rotation when they are flying? So please keep a number in your mind what you expect the speed of the shuttlecock to be, and you'll be surprised with the next slide. So we have recently done some experiments to measure the RPM of these shuttlecocks. So there are 3 different models. The blue line is the feather. The green line is the feather. And then the blue is the 2000 model, the Mavis 2000. And 350 is what most people play with the Yonex 350 shuttlecock. And please see this x-axis is the speed, meters per second and kilometers per hour. So these devices can spin at more than 10,000 RPM. Okay, and we've checked this again and again. And so they are spinning very quick. Okay, and in fact, there are now 2 opposing processes. So if your shuttle is flying, you hit a smash, it tries to kind of reduce the area, but because it is spinning, it tries to get fatter, because the centrifugal stresses. So there are these two competing phenomena, and clearly a lot of work needs to be done to come up with optimal things. But you still see this buckling now in the 350 at high speeds, although now the cross section is triangular and not square as we saw for a fixed shuttle. Okay, we now move on to other aspects. So I want to talk about cricket, which is what the title of the talk is. So I need to bore you a little bit with the fluid mechanics and then present to you some results on cricket. So if we take a sphere, just a simple smooth ball, okay, and ask ourselves how much drag does it experience because of the fluid flow. You can also think of an experiment where I take a sphere and a cannonball, and then I shoot this cannonball from a cannon and ask myself how far will it go, okay, and how much air resistance does it feel. Both are exactly the same problem. So in this picture, there are two curves. The red curve is the drag, the air resistance that the sphere experiences, and the x-axis is the speed or the Reynolds number. So here is the Reynolds number for you. So rho is the density, v is the speed, d is the diameter, and mu is the viscosity of the air. So if I take air, then rho and mu are fixed. If I fix the diameter of the sphere, this is also fixed. So you can think of Reynolds number changing only because of speed. Okay, so you can think of this as a speed axis. The y-axis is, of course, the drag. That's the red color curve. But we can non-dimensionalize the drag by the drag divided by the dynamic pressure, which is just half rho v square, and A is the cross-sectional area of the sphere, which is just a circle. Okay? So this is a better quantity to work with for fluid mechanics. Okay, now we come to the drag. So the drag typically increases quadratically with speed. In fact, those of you who are young and ride motorcycles, there's a message here. The drag, the air resistance increases square of speed. The power would increase with cube of speed. So if you increase your speed by 10%, your fuel consumption would increase by 30%. Okay, so that's maybe the take-home message. So drive carefully. And then at some point, the party is over. This drag doesn't increase as much. It suddenly goes down. Okay, so this is a weird phenomenon. What we are saying is, if I am throwing a cannonball from a cannon, if the cannon is thrown with this initial speed, it will go a certain distance. But if I throw it really quick, maybe 10% quicker, then it will go much, much further. So at a certain speed, the air resistance actually reduces. And the reason is because the boundary layer goes from a laminar state to a turbulent state. So this is a laminar boundary layer which separates very early. And this is a turbulent boundary layer. You can see a lot of randomness, a lot of mixing, but it separates much later. So as a result, the disturbance of the ball is in a much narrower region, and here it's a very wide region. So that's the red curve is the drag. If you look at the drag coefficient, then there's actually almost a constant drag coefficient up to a certain point. That's the critical Reynolds number. Then it becomes turbulent and it goes down. And then, of course, you stay at a low drag coefficient. Okay, so that's for a smooth sphere. Okay, so the message that I would like you to remember is, if I had a smooth sphere that I was using as a cricket ball, then the drag on it would keep increasing with speed, but beyond a certain speed, the drag would be much smaller. Okay, so that's why people make golf balls. So maybe I'll skip this one for lack of time. So what happens if you make this sphere rough? Does the same phenomena hold? So this was done by Professor Achenbach way back in 74. So this is the drag coefficient that I just showed you for a smooth sphere, the solid line. And then if you keep increasing the roughness of this sphere, it turns out the transition to turbulence can be controlled to a lower Reynolds number. So now you would get a lower drag shift at a lower Reynolds number. But the bad news is, this was the smallest drag coefficient you could get with a smooth sphere, but as you increase the roughness, that that benefit is gone. So you would get a smaller benefit of making the boundary layer turbulent. So now imagine if I was playing golf. If I was playing golf and using a smooth ball, so I take a golf club, hit the ball. So for the same force, my boundary layer would be laminar. I would be probably incurring so much of drag, and the range of the ball would be tiny. But if I am able to make the ball rough, let's say I make it rough with so much roughness, then my drag coefficient would be a lot smaller, less than half. So with the same force, the ball can now go further down. Okay. Of course, this would happen only in this regime. If the smooth was already turbulent, then making it turbulent further doesn't help. Okay. So a couple of things to remember. A, the roughness changes the boundary layer from a laminar to a turbulent state, and it has some benefits. B, this transition for a smooth sphere happens at this Reynolds number of roughly close to 500,000, whereas cricket is played usually at about 1/10 that speed. Okay, so there, if you took a cricket ball and there was no roughness on it, the boundary layer would definitely be laminar. Okay, so this is important because now by using the roughness, you can control the boundary layer from a laminar to a turbulent state, and hopefully we'll see that in the coming slides. So some history. This is your golf ball, a cricket ball, and this is a baseball. So two different games emerging from different continents, and look at the similarities. About the same diameter, 72 mm, about the same mass, 150 grams, 155 grams. Okay. This operates at about a Reynolds number of 10 to the 5th. Baseball is thrown underarm, so it's a little bit faster. And look at the golf ball, much smaller, higher speeds, and that also operates at about 2 into 10 to the 5th. So very similar range of Reynolds number. This picture is taken from Professor Mehta's paper. So Professor Mehta was a consultant at NASA. He's still very active. He's the one who worked with Imran Khan and Sarfaraz Nawaz and first worked on swing and reverse swing. Okay, so we've really built up on his work. So very grateful to him for that. Okay, now how does this translate to cricket? So with due apologies to Mr. Srinath, I don't know much, so please you will forgive me, but this is just more for my students. So you can tell me if there's something that I'm missing here. So as a batter, I want to whack the ball and hit it as far as I can. And as a bowler, I would like to deceive the batter. Okay, and what are the tools that I have? I could bowl very quick, so the batter has very little reaction time. The other is I could resort to spin. So spin actually has two aspects to it, at least two aspects to it. One is you get movement off the ground. So when the ball, because of the spin, hits the pitch, then it's going to turn. So that's quite straightforward in terms of the dynamics of the ball, not in terms of the skill of spinning the ball, of course. I think a bigger, for an aerodynamicist, the bigger intriguing thing is the movement in the air. So a spinning ball can actually move through the air. And I have a small video for you, which I like to show you. So that's called the Magnus effect. So if you have a ball which spins and you have a flow coming at it, so either the ball is going from, so you can think of the ball going from right to left, or you could sit on the ball and say the flow is coming at you, okay, from left to right. It's the same thing. So you have this ball spinning, so there's a retreating side which goes away from the flow, and there's an advancing side. And now these two are asymmetric. So that creates the force, and that's called the Magnus force. And of course, the drag is there. It's named after the German physicist. So I have a small video.
Recently, some friends of mine went to the Gordon Dam in Tasmania, which is 126.5 meters or 415 feet high. Then they dropped a basketball over the edge. You can see that the basketball gets pushed around a bit by the breeze, but it lands basically right below where it was dropped. Now watch what happens when they drop another basketball, but this time with a bit of backspin.
Whoa, look at that go! That's incredible.
You want days to get back in the water, do you?
Okay, sorry for cutting the video, but I need to speak too. So that's the Magnus effect. So when you have a spinning ball, then actually you can generate a force. And what the spin is doing is you can actually get the ball to move through the air. Okay, and you can use it in many different ways. But we are not going to talk about that in this talk. I'll give you a small glimpse towards the end, but that's not the main thing. You could also do seam bowling, where the seam is held vertical and then it hits the pitch, and actually it could go either way. So this is another way to deceive the batter. We are going to talk about swing bowling, and here actually you hold the seam vertical and it's probably pointing to one of the slips. So if I am a right-handed batter, then it could be pointing either to the off slip or to the leg slip and vice versa. And then I have to look at the seam and see which way the ball will move. So I'll show you the terminology that at least in the sports aerodynamics community is very common. Okay. So first the idea of in swing and an out swing. So for sports aerodynamicists, they are identical. Okay. So in terms of the fluid mechanics, I really don't make a difference between them. You'll see a ball that is pointing, the seam is, so if I'm a right-handed batter, this is pointing towards the off slip, so the ball moves in this direction, in the direction of the seam. This one is moving on the leg side. For me, both are conventional swing. Okay, so one is in swing, one is out swing. That's, by the way, as far as mechanics is concerned. So if I am a good batter, I am going to watch the bowler, okay, how they hold the seam position. And the bowler is trying to hide the seam position, not give it away to the batter. Okay, and but a careful batter would be able to make some guesses, and therefore he or she expects that the ball would swing in a certain way because of the seam position. But it could go the other way, and that we call as reverse swing. I don't know what the terminology amongst the cricketers is, but that is what the sports people who analyze it use it. So there are many questions. Okay, can a new ball reverse swing? What is the phenomena of swing and reverse swing? Can we control it? So on and so forth. What happens when the ball becomes old and so on? Okay. So these are very complicated questions that I will show you, but we've offered some answers in at least a very simplistic kind of a situation. So the first thing we did was do wind tunnel tests. Okay, seeing is believing. So we took these balls, the cricket balls, and put them inside a wind tunnel. So this is the National Wind Tunnel Facility at IIT Kanpur, really state of the art, one of the best tunnels in the world. One of the ways a tunnel is judged is by the turbulence it has. So this has a very low turbulence level, and of course there are reasons for it. Maybe someday I can talk to you about it. So here is a cricket ball, and the flow is going into the screen. So a wind tunnel is essentially like a room. So we could think of this as a test section of a wind tunnel. So you have a big fan, far upstream, and it drives the flow at us. So we keep a specimen here, and it would appear instead of the ball flying towards the batter, the air is flying towards the ball is fixed, and we can put this device on a balance, and this would measure all the forces, the moments, everything, and we can record it. Do some other experiments. I'll show you a few other things. So in this experiment, we have not spun the ball. We have kept it at a certain seam orientation. So this is like 30-degree seam orientation, which is very difficult for a bowler to bowl with. And this is the flow speed. So two variables, the seam orientation and the flow speed, and we see how these forces behave. Just to get you oriented with the notation, so imagine that the flow is going in. So the ball is, if you are a batter, the ball is coming at you. So if you are a right-handed batter and the ball is going to swing, then the ball will swing towards the off slip. Okay? So we are going to call that force as positive, so that's the conventional swing. If for some reason it goes the other way, that's negative, and we are going to call it reverse swing. There's also a lift on the ball. That's because of the rotation, the Magnus effect, and I'll talk about it maybe towards the end. But for the next few discussions, we'll not worry about this force. So we carried out a lot of experiments, and this is a summary of those experiments. Okay. So the x-axis is again the famous Reynolds number. You can think of it just as the speed Of course, you are not getting a sense of what these speeds are. I'll explain them in a few slides. This is the drag coefficient and this is the swing coefficient. Okay? So the seam angle is fixed at 30 degree. So we've put the ball in the wind tunnel, done a 30-degree seam angle, and then see what happens with the speed. Now, when we started doing these experiments, we realized all balls are different. They are handmade. Okay, so you do experiments on one ball, then you put another specimen, or maybe after a few days, maybe it's sitting on a table, it's got deformed, so you're not able to reproduce the data. That's no for science. Okay? So we said, okay, maybe we need to 3D print these balls. So we made AutoCAD models of them, 3D printed them, and then we could also look at the effect of 5 trips, because a typical ball has these stitches on them, 6 rows of stitches. We could also get it down to just 1 trip. For pressure measurements, we can make pressure ports. So we carried out experiments with a large number of specimens. You can see that qualitatively they all behave the same. Okay, so we'll just focus on the blue curve, which is the cricket ball. So here is the phenomena. If I make a delivery at very low speed, my boundary layer is very thick. That's the zone of viscous flow compared to the seam height. So the seam doesn't make any difference and my ball does not swing. So I get zero swing at low speeds. As I increase my delivery speed, the swing starts picking up and then it saturates, and at some point, boom, you go into reverse swing. Okay. So why does swing happen? So the answer is in this cartoon. So the flow is coming at the ball. The seam disturbs the flow. We'll call this as the seam side. So this goes turbulent. This one is shiny. It stays laminar. Actually, both sides are shiny, but this has no seam in it. There's no disturbance. It stays laminar. This one, because of the seam, becomes turbulent. So the separation gets delayed, as I showed you. There is more suction on it. So you get a force in this direction, and that's the swing force. As you keep increasing the speed of the ball, now this guy will also become turbulent at some point. Remember, I showed you even the flow on a smooth sphere will eventually become turbulent. So this guy was already turbulent, and now this guy becomes turbulent. But the bad news for this guy is, because it has been forced due to a disturbance, it is not as efficient. So the pressure here is not as low as it is in a natural transition, because it happened on its own. So this pressure is now slightly smaller than this pressure, and now you go through a reverse swing. Okay? And of course, if you would continue to bowl, you would keep getting reverse swing forever. Okay. So we try to do some experiments and try to figure out whether this hypothesis is correct. So we do something called an oil flow visualization. So we take a specimen, in this case of a black color, and we put oil on it, and in the oil we'll mix some kind of a white powder or a white dye. So when the flow is turned on, the oil is pushed back because of the shear stress, and this can tell you the black surface means there is no flow separation, and this point can tell you the separation. So from that we deduced what the flow is and confirm our hypothesis. We also did a lot of pressure measurements, but I will not bore you, just showing you that a lot of rigorous experiments were done. We did something called a particle image velocimetry to look at the flows, whether the boundary layers indeed are becoming turbulent from a laminar. So that was done. Okay. So if I am a bowler, when I deliver the ball, let's say I deliver it at 140 kilometers per hour. By the time it reaches the batter, the speed would reduce because the ball is incurring some drag. So I bowl at 140, but the batter may see only about 130 kilometers per hour. Which means if I want to track the trajectory of the ball, I should go towards a lower Reynolds number. So maybe if I start from here, by the time it reaches the batter, I would be over here. So we'll keep that in mind. There are a few questions that these experiments could not answer. We are very curious. So if indeed the boundary layer here is becoming turbulent, then this swing force should have seen a step function. It should have been 0, and when it becomes turbulent, it increases to a certain value and stays there, and then it becomes reversed, so it's again gets stuck at that value. Why is this going in a gradual manner? That we were not able to understand from the experiments with the limited data. So we thought it's again time to do the CFD. So again, we went to these different models, did CFD on them, large eddy simulation. So for that, first we did spheres, confirmed that the model works. Then we went to the cricket ball. So you can see very fine calculations. We resolved all the seam and everything. We put these on a parallel computer. So x-axis is the number of computers, y-axis is the speed up. So our code runs really quick. Okay, so we did these calculations now with the cricket ball and the seam, and with increasing Reynolds number, you can get all kinds of flows. So you can see slowly the flow is transitioning to a turbulent state. So this is a quiet flow, this is a turbulent flow, and so on. The outcome is the following. This is from an experiment, so maybe this picture is more revealing. So these are the flow visualization experiments, and this is CFD, and you can see amazing correlation between the two. Okay. So this is what we found. In a nutshell, I am going to explain you. So this is the Reynolds number. The blue line is from the experiments, and these solid triangles are from CFD calculations. Okay, it pretty much predicts everything. And what we found is that actually the boundary layer does not become turbulent to begin with. It stays laminar, but it's just delayed, and it actually becomes turbulent here. Okay, so the myth about the boundary layer becoming turbulent right at the onset of swing is not entirely correct. Okay, we checked whether the boundary layer is laminar or turbulent. We ran some diagnostics, so we confirmed it is not turbulent, and we are very happy this was accepted in a very prestigious journal. Okay, we constructed a history, and so I'll come to this slide now, which may be more interesting to you. Okay. So what is the effect of, let's say, weather from all this data that we have gathered? So let's take two bowlers. So we'll look at somebody like Mr. Saurav Ganguly from our generation, who would bowl at something like 80 kilometers per hour, and maybe somebody like Mr. Srinath, who could do 145. And let's see how they would perform at two different fields, one in Lords and the other in Eden Gardens. The difference is the temperature. We are assuming they are using exactly the same ball, SG Test cricket ball, not the Duke ball. And just the weather conditions are different. Okay, action is same, everything is same. Okay, let's go to Mr. Ganguly first. So in Calcutta, his Reynolds number would be something like 0.8 into 10 to the 5th. That is roughly here. So he would generate a swing corresponding to this. If he bowls in Lords, his Reynolds number would increase because the air is heavier, it's a colder climate. So his Reynolds number is 1.05, and he can swing the ball more. So with exactly the same action, everything same, he would swing the ball more in a lower temperature. Let's look at Mr. Srinath. So he bowls at Kolkata at 145. His Reynolds number is about 1.5 into 10 to the 5th. So that would be somewhere here. Of course, he will swing the ball quite a bit at his will. He goes to Lords. His Reynolds number is now 1.9. And boom, he can now reverse swing. Exactly the same action. Okay. Now I don't know if this is true, but this is what our science is telling us. And you can ask him for his remarks at the end. Some interesting thing that we found from this cricket ball analysis is, airplanes have wingtip vortices. So the way an aircraft generates lift is, you have low pressure on the top surface, a high pressure on the bottom surface, so the air would leak from the sides, and you get these very nice vortices. Hey, what about a cricket ball? I have low pressure and high pressure on the two sides. Okay, so if you see here, in this picture, the flow is coming from left to right. I have low pressure here, high pressure here. So my flow should actually go around the seam. So I must get wingtip vortices. Okay, so this was not known, and we were very curious to find this out. And lo and behold, there are wingtip vortices. Okay, So now your cricket ball would have wingtip vortices like airplane. If it is swinging, if it is reverse swinging, they would be of the opposite direction. I think that these are very important in fast bouncers. So if I am a batter and a ball is whizzing by, the acoustic signature that you get because of these vortices could also be an additional scare to the batter. That's my hypothesis. We'll hear from Mr. Srinath what he thinks about it. Okay, so we've got all this data now about force from CFD and from experiments. So with speed, this is the swing force and then the drag. So you can see you get a swing and then you get a reverse swing. These are seam angles, 10 degree, 20 degree, 30 degree. We can use this data now to estimate the trajectory just like DRS. Okay, so the bowler delivers a ball at a certain seam angle and then how does it go? So we've taken a seam angle of 20 degree here for demonstration. So these are the initial speeds. That's the pitch length, about 20 meters. So this is the bowler, that's the batter. That's the speed of the ball, and this is the lateral deflection along the pitch. So let's first look at somebody like 90 kilometers per hour. So by the time it reaches the batter, it's about 82 kilometers per hour. And you can see this is the deflection you get, almost about a meter. Okay? And this actually is agreeing quite well with some measurements that were made in South Africa. As you keep increasing the speed, you can see now the deflection is actually coming down. Okay, so many people think that if you bowl quicker, the ball will swing more. Of course, that's not true, because the time in which the ball is in flight is much smaller at larger speed. So there's an optimal time when you'll get maximum swing, and at very large speeds, you are going to get reverse swing. And there's a small range of speeds in between, where the ball is initially reversing and then straightens out and does swing, because I showed you the Reynolds number. So initially it reverses, then it starts swinging, and it will do some very strange curveball kind of things. In fact, this is the deflection at the end of the pitch, what the batter would see. This picture is just repeated from the previous slide. So this is the maximum deflection of about a meter. This is reverse, and you can get some kind of a curveball in between. What happens if I have a ball that gets old? So you must have seen bowlers, earlier they used to, but now they are not allowed to use spit and then polish the ball. Maybe Mr. Srinath will tell us. I have always worried which one is more effective, whether it's polishing it here or at the back. Maybe you can tell us something. My student asked me this question. I had no answer. So we tried taking old cricket balls from our students, but we were not able to get any useful findings from them. So we artificially sandpapered them to get the effect of ball becoming old. Okay? So here's a new cricket ball, and imagine that the team has decided the logo on which they will make the ball rough or keep it rough, the other side they will shine. So we do an experiment with this specimen. Then we actually turn it around, flip it, and do the experiment with this. So if the flow is coming from left to right, this is a new ball. This is like a 20-year-old ball you can think of, where now the seam side sees not only the seam, it's additionally rough. So the hope is this will become turbulent even earlier, so you will get an early onset of swing. Okay. This one is very interesting. When the non-seam side is rough, so it's just the ball orientation. The seam is trying to make the flow turbulent on the shiny side, but this rough side is also trying to make the flow turbulent. So now it's a competition. Who blinks first? Okay. So if your roughness is more, maybe this will become turbulent earlier. And if the batter is looking only at the seam, then you could actually get reverse swing in this at very low speeds. Okay. So we roughen it further, the seam, do experiments, and this is finally a complete rough ball. So this picture shows here different conditions of the ball. This red one is the new ball. We have already seen that. And this is the one I was talking about, where now the non-seam side is rough. And you can see you get reverse swing even at about 50 kilometers per hour. So spinners are able to get reverse swing. and then eventually the seamers are able to get a swing at large speeds, where with a new ball they would get a reverse swing. Okay. Of course, this should end at about 160 or so, so you can please ignore the rest of it. For computing, it doesn't matter. Okay, what does the spin do? As I explained to you earlier, usually the ball will spin just like a shuttlecock. So the bowlers, because of their action, will end up doing a backspin on the ball. So if you're a bowler, the ball is spinning towards you and flying towards the batter. So you could get swing, reverse swing, and typically because of the spinning action, you would get a Magnus effect, which would make the ball rise. So if I'm a quick bowler, the batter sees the ball rising and gets prepared to hit it. It turns out if this spin is very high, then you can get something called a reverse Magnus effect. So the ball actually stays low. So you get an aerodynamic force which is not in the positive direction, it's in the negative direction, and the ball will actually keep low. But this would happen in a very narrow window of speeds where the flow was laminar otherwise, and now because of spin you are making it turbulent. Okay, we can work out the details. So here is an example of a calculation. So you can see here so this is negative, this is positive. So you could get into a regime where you can actually get a reverse Magnus effect and negative. So I'm running short of time, so I'll skip these slides and just say a little bit about knuckleball and then stop maybe. Please watch this video. So this is a baseball, and you can see two things. A, the look on the face of the batter, and then the ball. Okay. Nobody has a clue what it's doing. Okay. So this is a knuckleball. So actually the ball is going through a very low spin. So normally when we pitch the ball, either a cricket ball or a baseball, it would have a backspin on it because of the grip. But if you throw it with your so-called knuckles, then there will not be a backspin on it. And if you are skillful, you can impart a very tiny rotation to it. Maybe it will spin one rotation during the entire travel across the pitch. Okay, and then it does this snake-like zigzag motion. We don't see that in cricket balls, but we use the term knuckleball usually for a slower ball. Okay, so I think we can make a cricket ball also dance. It can go zigzag just like this ball. And there's a proposal, a very humble proposal. So normally cricketers, they use the red trajectory where the seam is spinning when they bowl a knuckleball. So the seam is moving in a vertical plane. Okay, so the axis is in the horizontal. And this ball will not do any deflection, it will just go straight. But if you just change the orientation and you make the spin rotate along a vertical axis, then it will dance around. It will do very strange things, just like a baseball. Okay, so we published a paper on this, but we have data. So we did a lot of experiments. Okay, put this back in the wind tunnel and did experiments for all kinds of seam angles. So the idea is when the ball is spinning at a very low rate, the seam angle is changing during its trajectory. So you can see sometimes it gives a swing force in one direction, sometimes in the other direction, and it can do the zigzag. So we did all these force measurements, then translated them to trajectory. So here is a picture of a ball going through this knuckle. So you can see the seam is swinging, and this is the top view of the ball. So it is doing this snake-like zigzag motion. Okay, and in fact we tried to figure out what kind of deflections you can get and which would be a good rotation. So if the deflection is tiny, the deflections are large, of the order of half a meter here. But if the rotation speed is large, then you would have small deflections, but many of them. And in fact, knuckleballs in baseball, they are known to give only deflections about 10% of the diameter of the ball. Okay, so it's about 7 or 8 millimeters, or maybe 10 millimeters. So based on our analysis and our understanding of the game, apologies again for overextending, we think that if you bowl a knuckleball with about half a rotation and at about this speed, this would be an unplayable ball. Okay. Okay, I think I've exceeded my time, so I'll just show some slides on frisbee. Just go through them. So this is also a delight of a sports person. You spin the frisbee and it flies. And the question we were trying to ask is, what is the flow on the frisbee, and what is the role of rotation in the aerodynamics? Usually, the rotation is important for the stability of frisbee. You can see, I mean, it's really a fluid mechanician's delight. A very complicated flow. You get transition to turbulence. So we are working on this. I'll just show you the last slide here. So this is no spin. This is with spin. And we found that virtually the spin has no effect on the forces, even though the flow changes a lot. So that's a big one for us who work in fluid mechanics. So I'll stop here. I'll leave these conclusions. You can go through them. I've already exceeded my time. Thank you very much for your patience.
If anyone has a question for Mr. Mittal, kindly raise your hands. I'll bring the mic around. Thank you.
Sir, thank you for this wonderful talk. So my question was, you mentioned about the temperature, like how in lots the imparting of the swing would be more. So how does the kind of ball used would make a difference? Like a Kookaburra ball in Australia would, we've seen that it does a bit more, and the white ball that is used in ODIs and T20s is a little bit batter friendly. So the experiments that are carried out in the wind tunnel, are these like a baseline for all these kind of balls used, and what in that ball makes it do it that way?
No? Okay, excellent question, and I cannot promise a straight answer. I'll try to dodge you, swing you. So you are absolutely right. Seam has a very important role. Okay, so the thicker the seam, the more prominent it is. Of course, it will disturb more the flow, and therefore it will be more effective. Okay, so the stitching is different in the SG balls, the Kookaburra balls, and the Duke balls, and there is this difference. There is also a very slight difference in the diameter. There are two other big differences. The polish that is used, the lacquer. So you see, SG makes a pink ball and it makes a red ball. And I read some newspaper articles that the pink ball changes the aerodynamics more, and the color changes the aerodynamics. Of course, it's not possible. It's just that the pink lacquer is more smooth, so it results in a turbulence at a much larger speed. Okay, so those effects will also become important. I saw a video of Mr. Sehwag, where it's a very nice video, and I think Mr. Srinath must have seen him in person. Where somebody asked him that, Viru, what do you do when you open? And he said, I hit the ball because then it gets deformed and then the bowler is not able to swing it as much. And he said, then what do you do after it has become deformed? He said, I hit it more. So I think that sums it up. The deformation of the ball is extremely important. What we have done here is, for a new ball, we have chosen these balls carefully. They are almost spherical. But each ball has its own nuisance because they are handmade. So if you look carefully, they are not really spheres. I think good bowlers would be able to just look at a ball and eyeball it and see what it can do. So it can dance around. So if you take 10 balls, just like tennis balls, I mean, good players are able to choose a ball they want to serve out of a basket of 10 identical balls. Good bowlers would be able to, from experience and hard work, they would be able to choose a ball on how much it is deformed. So this seam business, getting old, is just part of the story. I mean, there is a lot more to that. The other question you asked was about, have I answered everything or this?
White ball and red ball.
Yeah, again the lacquer. The lacquer makes a very big difference.
No, my question was, I want to ask about the white ball and the red ball. Why does the red ball swing more apparently than the white ball?
I think we'll leave that to Mr. Srinath. He will address this. I told you whatever little I know.
So I wanted to ask, you mentioned that the flow is laminar at low speeds and then becomes turbulent. So why does the forces change when it becomes turbulent versus when it's laminar?
You know, you are inviting me to give another big lecture. I would love to do this, but I don't know people here are interested in that. But I'll try to unhide a slide that I reluctantly. My fingers are not as nimble as they used to be. Okay, maybe I'll just leave it like this. So actually what happens, if you take a body, then there'll be a high pressure on it. So if you think of this as a sphere, then there's a high pressure on it. That's because the air has come to rest. So we call that the stagnation pressure. If the pressure at the back of the body is also the same, then it will incur zero drag. So if I had a car where the pressure at the front and the back were identical, I could run it without any fuel, almost no fuel. Okay, but what really happens is this flow separates, and because of that separation, this pressure is high, this is low, and therefore you get a drag. In a laminar flow, the flow separates early, so that is shown here in the black line. Okay, so this is the pressure distribution. So this pressure here is really low. When you have a turbulent flow, then actually this is delayed quite a bit. It again reattaches. So the final separation point is here. So up to here it appears as if there is no flow separation. It's a beautiful flow, and it separates somewhere here. So this separation actually leads to a much higher pressure compared to that for the laminar flow, and that's the cause of reduction in the drag.
Question here. Thank you. Just one question. Among all the projectiles you have analyzed, cricket ball is the only one which bounces. And I see that even in your experiment, the bounce was not captured. Is it because it's aerodynamically not relevant, or was it something you have not captured? Thank you.
No. Very good question. I should have actually specified that in the talk. So thank you for bringing it up. Bounce is extremely important. Rotation is extremely important. Seam angle is not constant throughout. Okay, but these are some idealizations that we have made to start this work. Okay, and then we expect that this will get a little bit more inclusive as we go on. So bounce is amazingly important. In fact, there's something called a ground effect. So since you have asked, let me explain you a little bit. When airplanes are flying in air versus when they are flying at ground, their aerodynamics is very different. Just to give you a sense, when an airplane is very close to the ground, you can think of it that there's another airplane, an image of it below the ground, and together they create lift. So the lift you generate is much higher near the ground than in the far field. Cricket ball would do a similar thing. So the swing that I estimate, the other forces that I estimate, I think they are a little bit on the lower side. The ground will change them. Then there are these effects of turbulence and many others. So just the proximity to ground is very important. And bounce, of course, adds another dimension to it, the dynamics which we have not considered. So I don't want to say that the ground effects are not important, the bounce is not important. They are extremely important, but what can I do, sir? This is all we know right now. Moving towards that.
You mentioned that from a fluid dynamics point of view, in-swing and outswing are the same. Yet it seems empirically that most reverse swing is in swing, as in a reverse outswing is a rare phenomena. So might there be some plausible reasons that you have for why that happens?
I'm stumped. I'll pass that. I'll pass that to the expert. Sorry.
So my question is on badminton, a game that you've been playing. As a player, there are two parts to this question. There's a normal observation that a plastic shuttle starts off fast when you smash it, but by the time it approaches the opponent, it tends to get multiple speeds and towards a slowing down effect, as compared to a duck feather shuttle, which is far smoother. So can that be explained? Is it a perception or is it real? As one question. Two, also the court on which you play, whether it has another court on the other side, or it has a wall on the other side, whether those sides are also to be considered when you're looking at it from a speed and distance perspective.
Excellent questions. I mean, they are very relevant. So here's an observation that I have. Sometimes, my colleagues whom I play with, they will say, "Yaar, ye shuttle bhari hai, this is heavier." And I ask myself, what do they mean by a heavier shuttle? They are all 5 grams. Okay, so they cannot be heavier. I mean, they're all machine made, even the nylon shuttles. So I think a player, when they make some perception, it's actually the force that is required to hit the shuttlecock, and based on that they perceive many things. Okay, so the heaviness that we feel, the speed that we feel, sometimes it is related to the force that we are required to hit. So that's one way our perception is colored. You asked about the difference between the feather and the nylon shuttlecock. Indeed, they are very different. Okay, and I think the picture that I showed about the RPM, that is very telling. Let me just put that up.
So the question is actually relating to that the nylon seems to change its speed.
Right, that's exactly what I would like to show with this view graph. You are absolutely right. Yeah, this one. This is the one. Yeah, this is the one. So, so you can see here that the speed actually, if you look at the duck feather, which is the green one, it's a very monotonic behavior. Okay, so we call this as the advance ratio, the ratio of the speed of the tip to the translational speed. So that's almost a constant. Okay, that's easy to analyze. It's aerodynamically good. You look at the plastic ones. This one has a jump, a clear change in slope. This one is doing all kinds of strange things. Okay, so now imagine when I hit the shuttlecock, its speed is going to change. So I start with this speed. So I hit a smash. Maybe it's like 250 kilometers per hour. It is spinning and then the spinning speed, the RPM is going to increase as it slows down, right? And then decrease again. Look at the duck feather one. It just decreases all the way, and clearly this is now going to change the subsequent trajectory. So they are very different. On top of that, the feathers, they move actually. So their drag coefficient also changes, and when they are spinning. So the duck feather is very different than a synthetic shuttlecock. So your observation is on the dot. They are different. But can we explain this right now? No, we cannot explain this. Coming to your question about the size of the courts and the wall versus, essentially you're talking about the size of the badminton hall, which is a slow one and which is a fast one. Typically, if you have a single court, that will be fast, and if you have many courts, that will be slow. The reason being, so if I hit a shuttlecock, it energizes the flow also, the remaining flow. So if I have a small room versus a big room, that makes a difference, and the drag on it would be different. And of course, the air conditioning makes a difference as well. I don't think so, but it could. I mean, I would doubt it, but it could.
Hi, sir. I was wondering how significant the weight distribution plays a role in this, because I assume the shining of the ball has to do with, like, one is the surface area, how you deal with that, and the other thing is about the weight distribution also. So how significant that is.
Okay, no, good question. I've read some articles on the weight of the ball and some explanations given on internet about the change in CG. I don't quite agree with that. I think the CG doesn't change much. So if I have a given ball and I hit it around, the weight is not going to change much, and the CG location will not change. I mean, it will remain almost spherical. Of course, there will be some changes, but roughness and the shape will change. Shape is very important. Shape could be more important sometimes than the surface finish, but not CG.
I know there are several questions in the audience, but unfortunately we have to bring the Q&A to a close. If Professor Mittal is amenable, I'm sure you can ask him after the session's over. But for now, I'd like to invite Professor Sauradeep to introduce Mr. Srinath to the audience, not that he needs an introduction.
So, thanks a lot, Sanjay. I mean, this is really interesting because many of us relate to it at different levels, because I hardly know of any kid in the country who's not dreamt of becoming a cricketer at some little phase of their life at some time or the other. So of course, so this brings us to this part where I would like to request Mr. Javagal Srinath to come and speak to us. So, of course, I mean, he needs no introduction, but it's my duty and of course, a privilege to be introducing him. So he's a Mysuru-born cricketer, and as we all know, one of the greatest Indian fast bowlers. During the time of his debut, he was the fastest bowler India had produced at the test level, heralding a period of awakening of Indian pace bowling. And, so this was the side in the formidable 2020s fast bowler time. And he has represented India at various national and international level matches. And so 229 ODIs, 67 test matches, rubbing shoulders with other cricket greats. And this is a country that worships cricket. So Sachin Tendulkar, Rahul Dravid, Anil Kumble. I mean, I can go on and on. So Saurav Ganguly, Venkatesh Batra. He could hold his bat, and many in the audience would remember that the partnership he had with Anil Kumble, another of our Bengaluru, Karnataka cricketer, in winning the match against Australia as a batsman. He's, of course, an Arjuna awardee and has now is currently an ICC match referee, and he has had stints as a TV cricket commentator. But today, we would like to have him here and have his remarks on how he feels about this journey that scientists and with what we understand are trying to make into understanding what you guys, the magic that you do on the pitch, which we all look forward to watching. Thank you so much. Please.
Good afternoon, ladies and gentlemen. First of all, I'm really humbled to be in the midst of the scientists here. So I got to be very careful about what I speak in terms of technology, science, anything of that sort, because I won't get away easily here. Sanjay Mittal ji, you have done a wonderful job. First of all, the amount of work that has gone through, now I understand. मैं ground पे ही बैठा हूँ जी. It's a lot of work. I think I was just trying to correlate what happens in the form of science and technology, and then how do you correlate this to the game as such. It's quite different. It's very different. I think had I known these theories, I mean, for the first time, I'm trying to understand what is Magnus, what do you call that? Magnus effect. And then Reynolds number. I know Reynolds pen, but not the numbers here. So it's I think we have been playing with science with our own way on the field. But with these numbers, how to correlate is something that my mind is working now. Yes, I think the true value of, or in the end, these numbers are so important. I mean, we need to understand the tunnel effect, what you were talking about. I think there could be some scope for cricketers to understand this and then start working on it. I think a lot of work has been done. I think we need to still come to simple terms to the cricketers because we are not very, very smart when it comes to this. That bridge could be built to make us understand, how we could really better our efficiency on the field. Now, let me explain or probably the general way, the general cricketer's understanding of how the ball functions. What are the important aspects of a cricket ball? The first thing about the cricket ball is the seam part of it. Now, I might probably answer a few questions which you people been asking him in those Magnus and Reynolds way, but I'll speak it in my own way. I'll speak it up in my own way. Seam becomes extremely important. So let me start from how do we choose the ball. So whenever the toss is done, the fourth umpire would come to us with a box of balls. So he should come with 3 boxes of balls, which will be 18. So we pick up the ball. So first is the seam, the way you feel the seam in your hand. I wish I had a ball here, I would have shown you. Can I just have the ball here? So this seam becomes extremely important. I think for us, for any cricketer or any bowler, the first thing that he wants to feel of a ball is the seam part. Now, what does that seam means to us? The seam means symmetry between the sides. Okay, we expect the ball to be of the same weight on both sides. Okay, and we want the seam to be rough. I mean, really, it should be standing tall, which is missing these days with the white balls. With the white balls, now the seam has flattened. So if I rotate this ball here, if I roll this ball here, you can see the ball. Oh, sorry, I'm able to. Okay, let me do this here. You can see this, the ball there is a bump in the ball when it rolls. Whereas if you roll the white ball, you will not see that. It will probably go traverse in a very straight line. So the seam is missing. So let's come to how that has affected the bowlers is something that we'll discuss later. But let me just go with the normal swing. So the feel of the ball is extremely important for any bowler. So this decides why we need, in a team of 3 good fast bowlers, I think everybody will have a different way. So generally we look for consensus. After one of the guys choose the ball, one of the bowlers choose the ball, he'll pass it on to the other 2 guys to make sure that he also gets a good feel of the ball. So that's how the ball is selected. Now when it comes to the bowling part, so we choose the ball, now we go out and we bowl. There are so many factors that is affecting a bowler or his bowling. It could be the weather, it could be the temperature, it could be the pitch as such, it could be the moisture content in the pitch. All of it decides how the ball is going to behave on that particular day. The beauty of this game is that although you feel that the previous day and the day today is completely the same, still you might not produce the same kind of bowling what you did the previous day. Now there are some X factors which we don't know why that happens. Okay, back to the conventional swing. It all depends on your wrist action. So initially we believe that both the sides of the balls are the same. There's not much of a difference. So your wrist position decides what your swing is all about, how or what could be, in which way the ball could probably move. I had an action where my arm is close to the ears, more or less, and my seam position would be towards the batsman more. So which will probably give you a force behind the ball which is following the batsman. So that's an in-swinger. For example, Kapil Dev would probably, I would always try to keep the ball facing the batsman. Whereas Kapil Dev used to hold it slightly towards the slip, and his arm would be slightly away from his ears. Now what happens, you have stumps at both ends. Now the batsman is standing in front of the wickets. Now where the ball is being delivered, whether the ball is delivered right where the stumps are, where the bowler is, or somebody who uses the crease and then bowls into the batsman. Aim is to hit the stumps. So somebody coming slightly round arm will have to release the ball somewhere around middle stump of the batsman, or somebody like me will have to release the ball just outside the off stump. Now from there, we use most of the bowlers at all times will use the angle. We use the angle to get the desired swing. We can call it swing, we can call it seam, that can be interchangeable. Ideal situation is for you to bowl straight as possible, and after pitching, you got to seam the ball away or into the batsman. That's the one which is going to fetch you most of the wickets. If I am a batsman, and if I know the ball is coming from the edge of the crease and the ball is coming into me, it is easy for the batsman to play when the ball is coming predictably into the batsman. Or if somebody's bowling action is round arm, and if the ball is going away from the batsman, it is predictable and I can probably adjust my stance and then play the ball better. But if somebody is bowling straight, and which is stump to stump, because when you're moving the ball from edge of the crease into the batsman, it can hit any one of the stumps. When you're bowling outswinger, you are generally hitting the middle or off stump, because leg stump is very difficult to bowl. So ideal situation is you got to bowl straight, and where the batsman doesn't know whether the ball can come in or it can go out. Even the bowlers would not know whether the ball is going to come in or go out sometimes. These are the X factors. I still remember asking Imran Khan way back in 1991 as to, you as an youngster, you want to meet any big fast bowler, any great fast bowler, and I keep asking him questions. So I met him in the gym and he said, bowl 6 balls, try to master your stock ball, which is, the ball which is coming into the batsman. एक हाथ ball तो सीधा निकल जाएगा तो वो outswinger हो जाता है. So this is what he said. So that is how we learn. Then over a period of time, you will be able to, the grip gets better and you have enough experience. Depending upon the kind of pitch that you have, you can hold the seam and make the ball taut and move the ball the other way. Now this is the conventional swing. So generally, somebody who bowls both, that is in swing as well as outswing, so he would rather bowl straight and then try to get, so he's excellent in terms of his wrist position, and this wrist position will impart that force whether to take the ball in or to take the ball out. If you see England, what we call the banana swing, which means there is massive swing that happens. And for somebody who's watching on television, you will see the ball starting from here and then it goes all the way to the first slip. So you can see a big arc if you draw a line which goes nearly to the first slip. An in-swinger can come from here. It looks good, but it is not effective in terms of getting wickets. Okay, the more straighter you bowl, that much better it is for the bowler to pick up wickets. Now this is about the conventional swing. Now let's talk about the reverse swing. generally, whenever I'm asked to explain the youngsters about what is reverse swing, I just tell them it's the principle of a parachute. You throw the ball up, you throw the parachute up, the heavier side comes down, the lighter side stays stop. That's basically the gravity stuff. Even in reverse swing, it is the same. Okay, why does the normal swing, as I said, is more to do with your wrist position and the direction. Whereas reverse swing is completely opposite to that. Now, what does the reverse swing do? We start shining the new ball as well. Now, what happens when you shine with the new ball? There is a bit of sweat that goes into one side, and then you don't do anything with the other side. So when I was bowling, I was livid to make sure that the ball is handled carefully by every fielder who is handling the ball. They got to be careful. They cannot touch one side of the ball like this, but they need to make sure that they put the sweat and the speed, whatever it is, and then make sure they shine the ball nicely. That brings a bit of weight imbalance between A side and the B side. So with the new ball, generally the one which has more, say for example, this is the shiny side, which is probably more shiny and all of it. The dynamics of the ball is such that if there is, I would say 80% of the shine here, and there is still 100% of the shine here. And this 80% is basically we have not shined this side of the ball. So that's why I call it 80% of it. The swing is still the conventional one. Okay, so you give your wrist position, you give the right wrist under the ball and make sure that you direct the ball towards the off stump, and it's easy to bowl that swing. But as the ball grows older and older, one side you see the scruffs. Okay, the ball is almost coming up. Now what we want to do is, in Indian conditions, because of the abrasive nature of the pitch, what we do is we shine only one side and then allow the other side to be as rough as possible. We want that to be rough. I think that's where the doctoring thing came into picture, and then people started using those bottle caps to scrape one side of it. Now, more than shine, the ball that is damaged on the other side gives you better result for reverse swing. So that can happen probably from 40 overs onward, depending upon the kind of nature of pitch that you have and also the ball that is provided. So what happens when you really shine one side of it, that becomes heavier. So there is a differential weight on each, there is a differential weight on either side of the ball. So if this is heavier side, and if this side is the scruff part of the ball, so when you bowl, and there has to be a threshold speed here. So if your speed is less than 120, you will not be able to achieve that reverse swing, because in reverse swing, when you bowl, initially the ball will go towards the off stump and then it drags into the batsman. It comes back into the batsman. Where the problem happens for the batsman is, he is moved by seeing the ball going slightly away, so his whole position is this way. The moment, that is a natural movement of the batsman. So once he's stuck here, the ball starts coming in. So the ball starts drifting back into the batsman. So he's stuck with his footwork. And that's where the damage happens. And for the outswing again, now the shiny part will be the other side. Now, if you want to bowl an outswinger, I will keep the shiny part this side, because I want to take the ball away from the batsman. Now this is where we run with the ball with the other hand, so that the batsman should not know. Okay, we hide where we are trying to we were hiding the ball, making sure that the batsman doesn't see that. Good batsmen will watch this. Say, for example, Sachin and these guys, they know which side the ball is moving. So for him, I am now aiming at the leg stump. The moment I aim at the leg stump, the batsman is now committed to this. So that's when you're completely missing the line of the ball as it approaches you. So this is how the reverse swing operates. So basically the heavier side the ball starts drifting toward the heavier side, and that initial pace of 130 to 140 plus, it helps you to take the ball slightly away first and then start coming into the batsman. So that is the one which helps bowlers to get more wickets, and batsmen get confused with that little drift. Even spinners, smart spinners. So for all of it, the symmetry of the ball becomes extremely important. So when you bowl, if the ball goes this way, which Siraj does most of the time, but he's accurate. If you're accurate stump to stump, whether the ball is going seam-wise or if you have a rotating seam, doesn't really matter. But generally, the conventional way of keeping the ball, the seam upright is extremely important. So the ball, for any fast bowler, the moment the seam is, when you're bowling straight to the stumps, generally, if you want to bowl straight to the stumps, then upright seam is always good. And that's where the batsman is stuck, because it's coming in one straight line. The ball is more or less coming in one straight line. So the reverse swing is basically the heavier side. The ball is dragging towards the heavier side. And although you're pushing, reverse swing, when the ball is scruffed nicely on one side, my aim is to bowl at the 7th stump. Okay, I still remember playing a match in Goa, and David Johnson, unfortunately, he passed away recently. One of the lion-hearted fast bowler. So it was an absolute flat pitch. And I finished my first few overs, and then I was standing at mid-off. He came for the second spell, and he came to me and said, I'm bowling a normal swing, but it is going all over the place. I said, the ball must be reversing. He said, what do you mean reversing? I'm talking about 1995 types. I looked into the ball, and then I realized that, the ball is really reversing. So I told him, look, aim at the 5th stump. He said, what are you saying? That is not fair. Trust me, aim at the 5th or 6th stump, the ball will come in. And hold the ball like this, shiny side on this side, and I started shining the ball because I could see the other side was absolutely scruffed. So the first ball, it's natural, he bowled to the batsman. That's the way we are trained to do. The ball again went down the leg side, drifted 4. I said, no. Imagine there is a 7th stump here, and you're bowling at the 7th stump. And the very next ball, he was a round arm. Actually, it becomes even better because from here, you're creating an angle, this angle, and then the ball starts coming in. So for the batsman, initially it's an outswinger, and then it becomes an in-swinger. So the very next ball, he bowled a beautiful ball where the batsman had no clue, and it had taken the leg stump. And he was stunned. He looked at me and said, God, what's happening? I said, that is reverse swing. And he had tremendous energy. Fast bowling is more to do with the energy. And, he was young and he was able to bowl at good speeds. And then he got addicted to this reverse swing. A good question from the other gentleman there asking about reverse swing is generally the ball coming into the batsman, and outswinger doesn't have much scope in reverse swing. That is because the ball is old and the ball cannot travel all the way towards the wicketkeeper. Now, when the ball is reversing, which also means that the pitch is not carrying. The pitch, when it is abrasive, you will not have much bounce of the pitch. So you will never see a nice carry of a reverse swing. if you see the wicket keeper will not be carrying the ball here, it is always here, somewhere there, somewhere here. And in reverse swing is more effective because either you can get leg before or bowled, which is you have two options in reverse swing, or maybe a catch at forward short leg. Whereas the ball dies down by the time it reaches the wicket keeper. So what you do as an outswinger is to set the batsman up by bowling few outswingers and then get his movement going that way and then bring the ball in. So your dismissal will always be a leg before or a bowled in a reverse swing, and it won't be a caught behind. It's a very rare where you can get a caught behind. Not that it has never happened, it does, but generally the reliance is on bringing the ball in. So that's what happens. So, this maths is brilliant. This is too good. But I think from the cricketing point of view, I would say that there is more weight on this. That's the reason we want to put more sweat, more spit on this ball and start shine, put it in and make sure that this side is heavy where the other side is scruffed up. Now, even if I go a little more, if I use my engineering degree onto this one, I would say that there is least resistance here. So obviously the ball travels a little quicker, and therefore, because there is more resistance here of the air, so the ball travels in that direction. That's my thinking, and that has got me a few wickets. So this is more or less what reverse swing and my whole thing about cricket is that the wind factor. In stadiums, you don't get constant wind across the pitch. Okay, there are gaps, and then the wind starts coming through those gaps. Whereas when it is an open field, the dynamics changes completely. Okay, so there again, you got to do that little calculations on your own. Now, every body action is different. What that particular pitch, I'm talking about the nature of the pitch, the cricket pitch as well, the conditions, it could be 35, and the pace with which I bowl, all these things come together to give me that little advantage. Some other ground might give somebody else for his bowling, because bowling, in the end, it is all about your bowling action. If somebody says, okay, somebody is wiry and very slim, but he's able to bowl, like Ajit Agarkar, you could clock 140, and he was so wiry and thin. So it is nothing to do with the muscle. It is about the rotation of your shoulder at that particular point in time, what we call the delivery stride. So it all happens there. And then at that particular point in time, what is your wrist position? What we focus on entire career is how my wrist position is. If my wrist position is wrong, then you will never get the direction of the ball right. So it is always important to get the wrist position straight. I think, I would appreciate Shami for keeping the wrist straight all the time. So he always has a chance to come back because he's searching, because if Shami is not bowling well, you can look into his seam, it is scrambled. So what is he working on most of the time? How can I hit the seam straight? How can I hit the seam straight? That's exactly what he's looking for. And all the bowlers in the world who play test cricket would be looking to hit the seam straight. And all the bowlers in the T20s are trying to believe that, they want to believe that nobody's going to hit me. That's the difference between the white ball and the red ball. Red ball has lost it. During our playing days, the white balls used to have better seam. But what has happened now is that seam has vanished. So it's just a ball, and then there is no definition of the seam, what we can see. So that's the reason why you don't see pronounced movement, or bowlers can dictate terms. Of course, the flattening the pitch has also played an equal role in it, but I think more or less the seam has gone completely. And that is a machine stitched seam. Whereas this one, the ball which I have now in my hand, is a hand stitched one. So hand stitched one are always pronounced. And for any bowler, I think seam makes a big difference. So this is the one it is. And even for the spinners, it is very important to have a seam so that they can grip the ball properly. And if you see Anil always used to find that little drift. So the ball goes into the batsman and then spins away. Shane Warne, what they wanted was the ball to drift into the batsman. There again, the shine of the ball is extremely important and the position of the seam becomes extremely important. Even if you see when the ball starts coming like this, it is more effective for the bowlers. Then you can expect some drift and then turn, or a drift and seam of the pitch. So this is the practical stuff that what we go through and what we discuss. Now, whatever that we have discussed so far is what I have discussed with Dennis Lilly or Imran Khan, Kapil Dev and all these people. This is the language what we speak. This is all about the dynamics of the ball with me.
Thank you for sharing your experiences, Mr. Mittal. May I please request Professor Sauradeep to felicitate both of our speakers for today, please.
So I don't have words to describe this Jugalbandi, but one of the things I wanted to mention, as a responsibility as a scientist, is what I've realized in life over my whole career is the ability to talk across disciplines. And even as we were sitting and listening to Mr. Srinath describe, I think we are talking about the same effect, but the language is different. We have certain conventional languages, like if you look at social scientists nowadays, it's like, oh, that guy saps my energy, takes away my energy. As a physicist, you can't create energy or destroy energy, so it makes no sense. But you as a human being know what that person is trying to say, right? But it's just that in that state of mind, trying to describe it is beyond physics at this time. So we use different language. Similarly, in a field which has so much, so many X factors, people tend to use empirical language. You see what is happening and you try to build a story about it. Okay, this is what works. And ultimately, what matters is what works. And, as scientists, we try to put it in a language which we are familiar with. And one of the reasons we do these talks is to bring about this dialogue between different disciplines. And I'm so glad that, Srinath agreed to come here. And I hope we will have more such exciting discussions to bring to you. So it's my pleasure to, thank Sanjay first for his amazing talk. So this is biography of, and also Sanjay Mittal is Age of Physics thing of 75 years of RRI and 16 interesting cases. And again, I really want to thank you so much. It was a very special gesture in my mind to come up and sit through a science talk. And anyone who's been through the standard college, I completely commiserate that, you don't want to get into a classroom easily. So I'm glad you came in, and, here's something from the city. And this is, I hope you visit our institute soon, and there's a lot of exciting things happening there. My only request to
to C.V. Raman Institute is that I'm sure there are a lot of innovations that is happening not only here, but I think in most of the research institute across India. And representing the sporting fraternity, I would request, bring your innovation to sport. I mean, say for example, now we have Hotspot, which is one of the defense, it is a defense product. Now brought to the sport where it decides whether the ball has hit the bat or not. Such conclusive research, and if you have any of such products, it could be communication. I mean, we are looking for third umpire talking to the umpires at the center. Now that's a very sacred communication. We don't want anybody else to know. The moment if we go on the normal frequency, anybody can intercept. So if you have any of those communication equipment, which is, what do you call, encrypted. I think, see, those words should come. Encrypted and, secured in a frequency. I think, we need such products for cricket. It could be anything for that matter. I mean, the ball trackers, the way we track the ball. We need to bring it. And as research has to be implemented in sport as well. And cricket has grown to such levels. And I'm sure investment should not be a problem when it comes to cricket. And if the product is right, and I'm sure it will be accepted. So if there is any other products of that sort, and I will be the biggest proponent to bring it to the sport. So I'll be more than happy to do that. Thank you so much.
Saw you with the ball on the stage. It's a dream. Oh, you're a treasure. Okay.
On behalf of the BIC, I'd like to thank the Raman Research Institute, Professor Saurabhi, Professor Mittal, and Mr. Srinath.